So in this lecture of applied linear structures for computing, we'll start talking about eigenvalues, eigenvectors, and then based on these two very important definitions, we talk about different decompositions, such as LU decomposition, singular value decomposition, and QR decomposition, as well as eigen decomposition. The very first step to start this is understanding the definition of linear transformations. So in part one of this lecture, we are going to talk about linear transformations, as well as eigenvalues and eigenvectors. The goal of part one is to understand the definition of linear transformation. A linear transformation or a linear map is a mapping between two vector spaces, from vector space V to vector space W. Note that the dimension of these two vector spaces are not necessarily the same. So it could be from n-dimensional vector space to m-dimensional vector space. And it preserves the vector addition and scalar multiplications. What does that mean? F of, let's show our linear transformation as f from V to W. So f of u plus v is equal to f of u plus f of v. And f of alpha, which is an scalar, multiplied by u, which is a vector, is equal to alpha multiplied by f of u. So u and v are vectors, and alpha is a scalar. Example of a linear transformation, which is rotation by angle theta as a matrix in 2 dimensions, is A is equal to, matrix A is equal to cosine theta minus sine theta, and cosine theta. A linear transformation from a vector space onto the same vector space is called a linear operator. So f from V to V, this is a linear operator. Another example of a linear transformation is just a matrix with some values. A is 2, 4, 1, 0. So y is equal to ax. So A is called a linear transformation. Because if we apply A to x, it's going to lead to y. We can also show this as f of x. So f is our linear transformation. So we talked about this as a preliminary to introduce eigenvalues and eigenvectors. So the goal of this part is to identify and understand the definitions of eigenvalues and eigenvectors, see some of the useful properties and interesting features of eigenvalues and eigenvectors, and finally see some examples of how we can calculate eigenvalues and eigenvectors for a given matrix. So if T is a linear operator on vector space V, and x in V is a non-zero vector, and we have T of x is equal to lambda x, where lambda is a scalar value in the real space, then lambda is called an eigenvalue and x is called an eigenvector. We can represent our transformation by a matrix A and rewrite the above transformation as below. So we have matrix A, vector x, and a scalar lambda. Given all this, if A multiplied by x is equal to lambda x, then this vector x is called eigenvector of A, and lambda is called an eigenvalue of A. So usually we are given matrix A and we are expected to determine what are the eigenvalues and what are the eigenvectors. But the question is, how can we do that? So we start with AX is equal to lambda X, and then we bring lambda X to the other side of this equality. AX minus lambda X is 0. And then, because A is a matrix, we try to show this in the matrix format. AX minus lambda multiplied by I, which is identity matrix, multiplied by X is 0. Now we have matrix A and matrix lambda I. A minus lambda I multiplied by X is 0. And based on this, we simply put determinant of A minus lambda I to 0. As you can see in this equation, we eliminated the eigenvectors X. So this one is going to give us lambdas or eigenvalues. So using this equation, we can find eigenvalues of matrix A. And note that these eigenvalues are not necessarily just one eigenvalue or unique. Sometimes we have multiple eigenvalues for a given matrix. Geometrically speaking, eigenvectors are those that only change length by a constant factor under the transformation. So eigenvectors are not necessarily unique, but eigenvalues, we find the exact value for them if they exist. All right. There are some useful and interesting properties for eigenvalues. You can compute the determinant of a matrix by taking the product of all of its eigenvalues. Let's say I have matrix A, and it has n eigenvalues. We show the eigenvalues by lambda sub 1, lambda sub 2, and lambda sub n. So in order to find determinant of matrix A, instead of going over the complicated determinant equations, we can simply multiply all these lambda 1 multiplied by lambda 2 multiplied by lambda n. And if you want to show that in the compact form, this is how we represent it. So this means multiplying lambda 1 to lambda n. We can also compute the trace of a matrix by taking the sum of all of the eigenvalues. So let's say matrix A is A11, A12, A sub 13, A sub 21, A sub 22, A sub 23, A sub 31, A sub 32, A sub 33. So in this scenario, and let's say the eigenvalues of matrix A are lambda sub 1, lambda sub 2, and lambda sub 3. So in this case, trace of A is equal to A sub 1, 1 plus A sub 2, 2 plus A sub 3, 3. It is equal to lambda sub 1 plus lambda sub 2 plus lambda sub 3. And for the general case, trace of matrix A is sigma all of the eigenvalues, sum of all of the eigenvalues of matrix A. All right. Now that we know the features of eigenvalues, we also know how to find eigenvalues and eigenvectors. Let's take a look at some examples. Example 1. Let matrix A to be 2, 1, 1, 2. We want to find the eigenvalues associated with this matrix. So as we said, we have to solve this equation. A minus lambda I is equal to 0, where lambdas are unknown. So A minus lambda I is A minus lambda multiplied by I, or identity matrix, which is having the same dimensions as A. So it's 2, 1, 1, 2 minus lambda 0, 0, lambda. is equal to 2 minus lambda 1, 1, 2 minus lambda. This is what we have here. In the next step, we find this determinant. Determinant of A, B, C, D is AD minus BC. We talked about this in the determinant part of this lectures. So we have this determinant. Now we simply put this equal to 0. If you solve this, there will be two lambdas. Lambda is equal to 1 and lambda is equal to 3. So for each of these eigenvalues, we can find an eigenvector. How do we do that? By using this equation. Ax is equal to lambda x. So we know the value of x, 2, 1, 1, 2, a. We don't know the value of x, x sub 1, x sub 2. We know lambda. Let's say for lambda is equal to 1, 1, multiplied by x1, x sub 2. So one viable solution here could be 1 and minus 1. All right. For eigenvalue lambda is equal to 3, we get the eigenvector x lambda is equal to 3. So this is going to be our eigenvector. So if we have 2, 1, 1, 2, x sub 1, x sub 2 is equal to 3, x sub 1, x sub 2. In this case, we lead to this center. So these are the two eigenvalues that we could find. But any vector which is parallel with these vectors is counted as eigenvector as well. So if you multiply this vector by 2, it still counts as an eigenvector. And what's the reason for that? Because you simply can multiply both sides of this equation by 2 or by 3 or by any value that you want. So basically, if vector x or the eigenvector is multiplied by a constant factor, where the constant factor is non-zero, still the new vector counts as the eigenvector. Let's look at one more example to understand this notion, this concept that I just talked about more clearly. Example 2. So we define matrix A to be 0, 1, minus 2, minus 3. So we have matrix A. Step 1 is to find eigenvalues. How do we find eigenvalues? We find A minus lambda I. So A is 0, 1, minus 2, minus 3, minus lambda I, which is the same dimensions as A. So this is going to be minus lambda 1, minus 2, minus 3, minus lambda. All right. Then we set the determinant of this to 0, which means determinant of minus lambda 1, minus 2, minus 3, minus lambda is equal to 0, which is lambda squared plus 3 lambda plus 2 is equal to 0. Considering this, lambda 1 is minus 1, lambda 2 is minus 2. So we have these two values for each of our eigenvalues. All right, let's find the first eigenvector. A v sub 1 is equal to lambda 1 v sub 1, which means A is 0, 1, minus 2, minus 3 multiplied by v sub 1, 1, v sub 1, 2. Element 1 and 2 of v1 is equal to lambda 1 minus 1, again v1, 1, v sub 1, 2. So we simplify this side, which is going to be v sub 1, 2, and minus 2 v1, 1, minus 3 v1, 2 is equal to minus v1, 1, minus v1, 2. Now we bring this to the other side. So we have v1, 2 plus v1, 1 is equal to 0. And the other equation tells us minus 2v11 minus 2v12 is equal to 0. So both of these are basically the same. Or v11 is equal to minus v12. All right. So what does this mean? That means we can choose any arbitrary values for the elements of V. Let me choose K. So what does that mean? V1 is equal to K and minus K, where K is non-zero. So you choose any K, and this is going to be your eigenvector. Let's say K is equal to 1. So our V1 could be 1 and minus 1. Let's say K is equal to 2. Then our V1 is going to be 2 minus 2. Let's say K is minus 1, then V1 is minus 1 and 1. So as you can see, these are all eigenvectors for this matrix. All right. So we want to find the second eigenvector. We already have one of the eigenvectors. Let's see what's going to happen for the second eigenvector. So I'm going to remove everything and have matrix A written again. Matrix A is 0, 1, minus 2, minus 3. Lambda 1 was minus 1. And the corresponding eigenvector V1 was K multiplied by 1 and minus 1. Lambda 2 is minus 2. Let's try to find the eigenvector for this one. So I'm going to give a 2-minute break here. So you spend some time and try to find the eigenvector corresponding to lambda 2 using this equation. All right, now let's take a look at the answer for this. So we have A 0, 1, minus 2, minus 3 multiplied by V2, V sub 2, which is V sub 2 element 1, V sub 2 element 2, is equal to lambda 2, which is minus 2, multiplied by again V sub 2, V2, 2, V2, V2, 1, V2, 2. All right, so this is V2, 2 minus 2V2, 2 minus 2V2, 2 minus 2v21 minus 3v sub 22 is equal to minus 2v21 minus 2v22. All right, so bring that to this side. You're going to have v22 plus 2v21. We have minus v22 minus 2v21. This is equal to 0. So first equation tells us v22 is minus 2v21. Second equation tells us the same thing. v22 is minus 2v2. All right. Then our v2 looks like, let's say v21 is k. If v21 is k, then v22 is minus 2k. Or this is equal to k multiplied by 1 minus 2. All right. So if you recall, v1 was k multiplied by 1 and minus 1. Let's call this k sub 1 and call this k sub 2. So these are the two eigenvectors. One specific scenario for eigenvector that we are usually interested in is eigenvectors that their dimension is equal to 1. What does that mean? That means k1 is equal to norm of v1, or 1 divided by 1 divided by norm of v1, 1 divided by 1 plus 1, or 1 square root of 2. So, and same here. So we can choose k2 to be 1 divided by the norm of v2. We somehow normalize v2. So it's going to be 1 divided by square root of 1 plus minus 2 squared, 1 divided by square root of 5, which means our v2, the normalized version, is 1 divided by square root of 5 minus 2 divided by square root of 5. Again, this is not a mandate. What we have as eigenvector is any of this with any chosen value of k sub 1 or k sub 2. However, in some specific scenarios, in order to have a standard, in order to have a unique answer, we can choose our eigenvectors to be normalized vectors with dimension 1. In that case, we find the norm of those vectors and choose k, or the multiplier, to be inverse of that value. All right. So this was how we can find eigenvalues and eigenvectors by hand. I wanted to give you an intuition about what is the concept behind eigenvalue and eigenvector. But in Python, you can use the NumPy library, linear algebra, and this script, numpy.linearalgebra.eig of your matrix. This is going to give you W and V. W is a vector that includes all of the eigenvalues, is a vector of eigenvalues, and V includes the eigenvectors. So W actually is all eigenvalues, first eigenvalue, second eigenvalue, third, and so on. In MATLAB, however, we have V and W. So we say V and W is equal to Eig of matrix A, and it can be used to find eigenvalues and eigenvectors. So V here is a diagonal matrix, which means all these are 0, where lambdas are on the diagonal. Lambdas are the eigenvalues of this matrix. And W, again, is a matrix. Each column of W is an eigenvector. So the first column of W corresponds to lambda 1. So lambda 1, V1. And the nth column corresponds to n. Second column to lambda sub 2, and so on. So this is how we can find eigenvalues and eigenvectors in MATLAB and Python. And this is how we want to use data for different types of decompositions you're going to see in the future. So you have a large matrix that includes all of your data set. You want to find the eigenvalue and the eigenvector. You simply use these commands in Python or MATLAB to find these two important factors. All right, this was a quite productive lecture. We talked about linear transformations. And based on linear transformations, we said that for a given matrix A, which is a square matrix in our case, a square matrix, which means its dimension is n by n. We say A lambda is equal to AX is equal to lambda x. Then we call X eigenvector of matrix A, and we call lambda eigenvalue. Then we said how we can find eigenvalues. How can we find them? Determinant of A minus lambda I is equal to 0. This gives us the lambdas. And based on this, we can find the X or eigen vectors. Then we talked about some examples of finding eigenvalues and eigenvectors, as well as how to find eigenvalues and eigenvectors in Python and MATLAB. This is somehow the basic for the decompositions that we are going to talk about in the follow-up lectures. So I suggest spend some time and understand all of the details that was discussed in this lecture.